webinar, and our topic is today is analysis of ChaCha, an encryption scheme used by Google. And our speaker for today's webinar, Dr. Sabyasachi Dey, who is working as an assistant professor in the Department of Mathematics, Birla Institute of Technology and Science, Hyderabad. He earned his doctoral degree in 2018 from IIT Madras and completed his master degree in mathematics from 2015 from IIT Madras also. He has published various research articles, book, chapters, conference as well. And Dr. Dey, we are so fortunate to have you here. So I would like to request you to deliver a talk. So please start, Dr. Sabyasachi. Now you can share your screen. So
Okay. So am I audible?
Yes, you are audible.
Okay, so I'm sharing the screen. Okay, is it visible?
Yes, it is visible.
Okay, so thank you, Paresh. So at first I would like to thank Paresh and the entire organizing team for giving me this opportunity to give this talk. And I will also thank all the people who are attending this webinar. So I'm going to talk about ChaCha. This is an encryption algorithm which is recently being used by Google. So those who don't know what an encryption algorithm is, for them, I will at first give a brief idea. So I think most of you know what an encryption algorithm is. So in our digital world, whenever we are sending some message to someone, it should be in a form so that any third person, if he can access the message, he actually cannot get the actual message. Right? So for this purpose, what we do is, instead of sending the actual message, we send an encrypted form. And for this purpose, we use several algorithms. There are many algorithms available in the market which are being used for this encryption purpose. So various companies and our defense and everywhere we can see this kind of algorithms being used. So ChaCha is one such algorithm. It was designed in 2008, and in 2016 it was adopted by Google for their encryption purpose. Okay, so I will start. So this is the outline of the talk. I will start with the basic principle of a symmetric key cipher. How does a symmetric key cipher works? Then I will introduce something called a stream project and another cipher salsa. Then I will come to the structure of ChaCha. How does the ChaCha cipher works? And then I will discuss where is the efficiency of this design. And after that, I will come to the research works which has been done so far and what are the future research works in this direction. Okay. So let's start the talk. So I will first start with the general idea of a symmetric key cipher. Right. So suppose there are two persons. I call them A and B. They are communicating through some insecure channel. Insecure channel means whatever message they are sending each other, that can be intercepted by a third person. Okay. Now in this situation, I have already mentioned that we use ciphers. So what these ciphers do, they encrypt the message to a form so that any third person cannot get the actual message. Okay. So here in this picture, you can see something called a plain text, which is the actual message. Now using some key and some algorithm, we encrypt it. The lock sign shows the encryption, and after that what we achieve is the cipher text. This is the form which is going from my device to the other party's device, and this cipher text, if it is intercepted by a third person, he cannot get the actual message because the actual message is the plain text. Right? Now whenever this is going to the other party, he has the same key, and using the same key, he is getting back the actual plain text. Okay, so this is the entire idea of a symmetric cipher. The point you have to observe here is the word symmetric. The symmetric means here that the key that we are using here for encryption is the same key that is being used by the receiver for decryption. Okay, so this is basically similar to a real world lock and key. We use the same key for locking and unlocking. So this is the same thing, but there is another category of cryptography which deals with asymmetric key cipher, where the key that is being used for encryption is different from the key which is being used for decryption. So they work in a pair. Okay, so both the symmetric key and asymmetric key, they have their own benefits and disadvantages both. So I'm not going to go to the discuss those parts. So I'll come to our topic, ChaCha. So in the symmetric key cipher, there is one particular category which is called stream ciphers. Okay, so this what these stream ciphers do? They are primarily designed for encryptions where speed is required, where you have to encrypt very fast. Okay, so this is how a stream cipher works. Initially, A and B, they share a small number which is called key. Key is a secret number which is shared between the sender and the receiver. Okay, this is known to the sender only and the receiver only and nobody else. Now, there is an algorithm which is the stream cipher basically. The job of this algorithm is it takes the key as an input, so it's like a function, and as an output it generates a sequence of numbers. Okay, so this sequence of number is denoted by Zi. Okay, so this Zi, this is called pseudorandom key stream. Pseudorandom because it's not actually random, because it is coming from a cipher, some algorithm is used. But it is pseudo-random because apparently if somebody looks at this sequence, he will not be able to figure out any pattern in this Zi. So this is what the stream cipher does. It takes the key as input and the Zi as output. Now this stream cipher, the algorithm is available to everyone, but the key is a secret. So only those who has the key, that means the sender and the receiver, they have the key. Only they can generate the Zi and nobody else. Now, after this, what they do is they have the initial message that A wants to send to B, that is denoted by MI. It's a sequence of 0 and 1 only. Now, in the encryption phase, this MI is XORed with this Zi. XOR means addition modulo 2 bitwise, and some ciphertext is generated that is shown by CI. So instead of sending the MI, this CI is sent to the other party, right? And the other party has the same Zi, so he can get back the actual MI from this CI. Okay, this is the principle of stream cipher. Now, therefore, one thing you can very easily observe here is this Zi. This is the sole reason of the security of the message, right? If any third person can find out any single bit of this Zi, then he will be able to find out the corresponding bit of MI, right? Because CI is available to everyone. I mean, CI is available to the attacker. If somebody is intercepting the call, he can get CI. So only way to protect MI is that Zi should not be predictable, right? So the entire security depends on this Zi, and Zi is generated from the stream cipher using the key. Okay. Now in the market there are many stream ciphers available, but particularly why Google has chosen this cipher ChaCha. So before going to that, I will show a screenshot from the Google support page. Here you can see the list of ciphers that they are using. Here you can see AES, which is another famous cipher and being used by Google. AES 128 key-bit, AES 256 key-bit, and ChaCha. So we are talking about ChaCha today. So these are the three primarily used symmetric key ciphers by Google presently. Okay, so I will start before going to the description of ChaCha. I will start with this project, eStream project. Okay, so this eStream project was organized in Europe in 2004. The purpose of this project was to get some new stream ciphers, because in the market, all those stream ciphers available at that time was becoming weak. That means different types of weaknesses of the stream ciphers were being discovered. Therefore, those are becoming vulnerable. Now, since we have to protect our data in future, so this community decided to arrange a project where many designers from all over the world will send their design for stream ciphers, and those designs will be analyzed throughout the project. And after that, some designs will be shortlisted for future purpose. So around, I think, more than 100 designs were submitted in this entire project. It was this project ran for 4 years, and there were more than 3 phases. And at the end, 7 stream ciphers were shortlisted in this competition. Among them, in the left-hand side, you can see these 4 names: HC128, Rabbit, Salsa, and Sosemanuk. And in the in the hardware category, these are 3 ciphers, which are Grain, Mickey, and Trivium. So all of them are very famous ciphers. I am particularly going to talk about this salsa because salsa is because the ChaCha is basically a variant of salsa. Okay, so salsa was discovered in it was designed in 2005 by a person called Daniel Weinstein, and it was a candidate for this stream project. It has 20 rounds, but the author submitted the 12 round version only. Round means this is basically iteration. So inside the algorithm, we repeat the same operations. Each iteration is called a round. Okay. Now the author has submitted 12 round only, and it was selected. And this salsa uses a key of length 256 or a key of length 128. Okay. So salsa was designed in 2005. After 3 years, ChaCha came to the picture. ChaCha is a variant of salsa and designed by the same person, Daniel Weinstein, and he designed it in 2008. And what he did in this ChaCha was he made this structure of ChaCha is almost similar to salsa, but there are some basic modifications, okay, in the design. And interestingly, so far only up to 7 rounds it has been attacked. That means it has 20 rounds. The original version has 20 rounds. As we increase the rounds, more security comes, and less the rounds, less security. So far only up to 7 rounds it has been attacked. This is the reason why Google has decided to go for this cipher. This is a screenshot of a news in 2014 where Google was moving towards ChaCha. This news shows that initially there was a cipher called RC4, which was it was a famous cipher also. It was being used by Google for almost 20 years. Now after this, Google has moved to ChaCha, and 2016 Google has permanently adopted ChaCha for their encryption scheme. Okay. So let us discuss the structure. How does the structure looks like for ChaCha? So it starts with a matrix of size 4x4. Okay. So in this matrix, so 4x4 means it has 16 cells, and each of the cell contains a number of size 32, a binary number of size 32. Okay. Now, what are those numbers? The numbers in the top row, which I am showing by C0, C1, C2, and C3. These are some constant numbers given by the designer Weinstein himself. Okay. These numbers cannot be changed. In the next 2 rows, K0, K1, K2 up to K7, these are the key. So in the key, you have seen that there are 256 key bits. The key is of length 256. We break it into 8 parts. Therefore, each of the part contains 32 bit, right? So those 32 bits we call first one as K0, second one as K1. Like this, we go for up to K7. So those keys we put in the second and third row, and in the fourth row we put something called counter and IV. This T0 and T1 are counter, and V0 and P1 is IV. The purpose of this counter and IV is this is not secret. Like key part is secret, but T0, T1 and V0, P1 are not secret. These are variable which is known to common people. The purpose of these 4 values are that if we even keep the key same, even after that, by changing these values, we can change the output. So that using the same key, you can generate different type of outputs. Okay, that is the purpose of this IP. So what we do with this matrix? We apply some function on it, some operations. These operations are called quarter round. So what is this quarter round? It has 3 types of operations: one addition, XOR, and rotation. So what this quarter round function does is it takes a 4 tuple A, B, C, D and does some addition, rotation, and XOR operation on this, and generates another tuple A double dash, B double dash, C double dash, and D double dash. Okay, so the input is a 4 tuple, the output is another 4 tuple. This function does this job. Now this function is applied on each of the columns first. Okay, so in the right hand side you can see the columns are being applied by QR function. Okay, so after applying this quarter round function on each of the column, that is my first round. In the second round, the same operation is applied on each of the diagonals. So the yellow part shows the one diagonal, green part shows one diagonal, red part shows one diagonal, like this. Alternatively, in each round, in one round, the operation is applied on the columns, and in the other round, the operation is applied on the diagonals. This keeps on going up to 20 rounds. Okay. So after every round, we get a new matrix. And in this way, we keep on going up to 20 rounds. And at the end, what we do is we take the final matrix and the initially saved matrix, we add them by usual matrix addition and get the Z. This Z is the output key stream bit. This Z is the thing that we store with the message and get the cipher text. Okay. So this is the design. Now I will come to the discussion what is the efficiency of this ChaCha? Why? I mean, looking at the design, why can we say that this design is an efficient one? Okay. Now this ChaCha belongs to a particular category of ciphers, stream ciphers, which are called ARX. Right? ARX stands for addition, rotation, XOR. So all those operations of all those ciphers, there are many ciphers which are using only these three operations for their encryption. So ChaCha is one of them. So here this addition is basically addition of two numbers modulo 2 power n. That means if there are two n-bit numbers, their sum will also be n-bit. If in case it goes beyond n-bit, then we reject the first bit and keep it n-bit as it is. Okay. And the second operation is the rotation. That means we just rotate the numbers. And the third operation is the XOR. We know what XOR is. It's bitwise addition modulo 2. Now only using these three operations, ChaCha is providing a secure communication. Now the question is, what is the reason of the efficiency of ChaCha? Right? Now, when we talk about the efficiency of ChaCha, we keep in mind two things. First is the speed, how fast it encrypts. Second is the security, how much security it provides. Right? Now, usually, if we use more complicated operations, then speed decreases. Right? But at the same time, the security increases because for the attacker also, it becomes difficult to detect some weakness. Right. So more operations means more security, but less speed. But our ultimate aim is to provide something which has both speed and good security. So for this, it's a challenge for the designers that how to provide a design which is fast but also secure. Right. Now, ChaCha is a design which does both the job. The reason is, let's first talk about speed. Why it is fast? Because if you look at the operation, it has addition, rotation, and XOR. In each quarter round, in each row or column, we have 4 additions, 4 rotations, and 4 XOR. So 16. So if we look at the entire set, then we have 16 addition. Entire matrix, we have 16 addition, 16 rotations, and 16 XOR. Now all these operations are CPU friendly, because these operations are already saved in the CPU. CPU knows how to add, how to XOR, and how to rotate. Okay, this is why, and these are all simple operations. So this is why whenever we put such a cipher in our machine, it is very easy for the machine to compute. This is why machine is very fast. But if we compare it with any other cipher, let's take for example, AES. AES is another famous cipher which is being used in market, also by the Google. In AES, we have some operations like byte substitution, where you have a table. From that table, you have to find out the position of my byte and get the corresponding number and then put it back. Then we have something called mixed column, where you have to multiply it with a matrix. Now, a matrix multiplication itself is a complicated job. Then we have operations like shift row and key expansion. There are so many things involved in one round of AES, but compared to that, ChaCha has some additions, some rotations, and XOR only. This is why ChaCha is comparatively faster than AES. I am not claiming anything about security, because we cannot compare the securities in this manner, but definitely ChaCha is faster. Now, I have already mentioned that any design which has simple operations, those are fast, but at the same time, those are vulnerable, because for an attacker also, simple designs are easy to attack. Now the question is, why ChaCha is, instead of having such simple design, why ChaCha is secure? Now, for this explanation, I will give one example after this. But let's first look at this, what happens when we combine an addition operation with a XOR operation. Right? Suppose there are two numbers, x and y, both are n-bit numbers. Okay, I write them in concatenation form, x n minus 1, concatenation x n minus 2, like this up to x0, and y is y n minus 1, y minus 2, like that. Now look at the addition operation x plus y, and also look at the XOR operation x XOR y. If we want to find a relation between the sum x plus y with, now let us use the variables x and y. Okay, If we use the variables x and y, then z means suppose z is equal to x plus y. So x plus y is a very simple operation, definitely. But using this variable x and y, x XOR y becomes a very complicated operation. That means algebraically x XOR y means nothing. X XOR y is a simple operation where we write that in concatenation form. But if we want to solve by algebraic equation using XOR, using the variables x and y, it is a very complicated operation. It's a highly non-linear operation, right? Right. So that means XOR operation is complicated when we complicated to deal with algebraically when we use the variables x and y. But when we use, let us use the variables x1, x0, etc. for each of the bits separately. Then XOR becomes easy, right? Because XOR basically what it does is it goes to each of the column and adds xi and yi and gets zi, right? So each of the column has no influence over the other columns, right? So if we introduce a variable for each of the columns like x0, x1, x2 up to xi, then each of the zi is simple. Zi is basically xi or yi. Then these become simple, right? But then addition operation makes a problem. Why? Because if you look at the addition operation, when we add two numbers, there is a carry involved, right? Now this carry is not a simple function. It is basically a complicated function which involves all these bits in the right side, right? Because if you remember how when we add two binary numbers, the carry that is generated, that is not only our output of xi minus 1 and yi minus 1, because it also depends on the previous carry, and that carry depends on the previous carry. In this way, all the variables in the right side, from x0 to xi minus 1 and also y0 to yi minus 1, all the variables are involved in the carry function, right? So if we use this xi, yi notation variables, then addition operation becomes a very complicated function. And if we use our usual xy variables, then XOR operation becomes a very complicated function. Okay, so whichever approach we take, one operation becomes a very complicated nonlinear function, which is difficult to deal algebraically, right? This is why if we combine these two operations, addition and XOR, then whichever approach we take, whether we take x and y and z, that also becomes difficult to deal with. Or if we take these bitwise variables, xi minus 1, etc., that also becomes difficult to deal with. Because whichever approach we take, one operation differentiates, one operation provides a security. Right. I will explain it further by a simple example. Just look at this equation, x plus 4 XOR x. It is a very simple equation. Now, let me suppose you are given that x is a number between 0 to 15. That means x is a 4-bit number, okay, in binary. Now, if I ask you, can you tell me whether this equation has a solution or not? Okay. Or if I ask you what is the solution, if there is a solution, how will you deal with this equation? There is nothing you can do, because this XOR operation we can only perform only if we know the value of x plus 4, right? But we don't know the value of x plus 4. So even if it is a simple operation, we cannot simplify it further. The only way we can find a solution is by randomly guessing the values of x. Okay. Now just think about it. If we give an equation using addition and multiplication, we can solve it very easily. Just replace this XOR with the multiplication, it will be easy to solve. Replace the XOR with minus or subtraction, it will be easy to solve. You combine subtraction and multiplication, that will also be easy to solve. But whenever we are introducing XOR, also if we take two XORs, like x XOR 4, XOR x, that is also easy to solve. But whenever we are combining addition and XOR, it becomes so complicated because we cannot further simplify it, however small it is. The equation, however small it is, we cannot further simplify it. So this gives an explanation why a combination of addition and XOR operation is very secure to deal with. For any attacker, it is very difficult to deal with something like this algebraically. Okay. So this is one explanation. This is why RX functions are very fast, but they are not. They are also very secure, because this addition, if you look at the point of view of a CPU has almost takes almost same time to perform an addition or multiplication or XOR. So for a CPU to perform an operation like this is very simple. It is equivalent to perform two addition operations or one addition or multiplication, etc. Whatever we take, two operations we have to perform. So it is fast, but it is difficult to attack. That's what I'm trying to say here. So this is why ARX ciphers are very famous nowadays, and there are many ARX ciphers available, not only ChaCha. Okay. So that's the reason of the security of ARX type of design. So next I will try to the cryptanalysis. So what do we mean by cryptanalysis? So in market there are many ciphers available, right? Now how do I know that a cipher is secure or not? So to know that, what is done in the community is, when somebody proposes a cipher, everyone else tries to break it, because there is no guarantee that the cipher is secure. So the only way to check whether it is secure or not is that let us try to break it. If you are able to break it, then it is not secure, and if you are not able to break it, then it is secure. So this is based on the assumption that there are more good people on the earth compared to the bad people, so that before a bad person finds out the weakness, if the good people are able to find the weakness, then we can find some countermeasure. This is like the ethical hacking. If you look at the ethical hacking, what they do is they try to attack their own system, and they try to find any weakness in that before any wrong person finds the weakness, right? Because if everyone tries to find the weakness, it is expected that the good person will find the weakness first, because there are more good people on our planet. So only based on this assumption, all the ciphers are being cryptanalyzed all over the world, and only after a long period, if it is observed that some cipher is still secure and nobody are able to find any weakness, then it starts being used by common people or government or different companies. So this is exactly what happened for ChaCha also. It was it was designed in 2008, but in 2016 Google decided to adopt it, because for that 8 years it just observed how much secure as it is. If somebody were able to find any weakness in ChaCha, significant weakness, then definitely Google would have not been gone for this cipher. So what kind of analysis are done? What kind of weakness we are observing on ChaCha? So there's one well-known attack approach, which is called differential attack. So in this attack approach, the attacker, the third person, we assume that the attacker has the access to the machine, but he doesn't know the key. So he tries to find the key. So he has the access to the machine, so he can change some positions, he can give some inputs. I have discussed about IBM counters. So on those he has the access. So the attacker has the access on the IBM counter. So let us assume that the X7 is the IP. So what he does is he takes two matrices instead of one, and in one matrix X dash he changes one single bit from X. So X was the initial matrix, he changes one single bit. Then he runs the cipher in both the matrix. Okay. So as the matrix will propagate, we have seen that the round operation, as it will propagate, as the cipher will propagate, the difference will also propagate throughout the matrix, right? So the red elements are showing the positions where the difference is there. As the round is propagating, the difference is propagating throughout the matrix. So after some time, the two matrices will be entirely different. Okay. Now the attack approach is, as long as we can find some relation between X and X dash, we can say that we can distinguish this cipher from a random generator, right? Because in a random generator there should not be any connection. So if we can suppose at third round, we can observe that at up to third round we are able to find some connection between X3 and X dash 3. Then we will say that up to third round this cipher is distinguishable. This is a weakness of the cipher. Okay. So far on ChaCha, only up to fifth round it has been observed that it is distinguishable. Okay. So using this differential attack approach, the first attack on ChaCha was proposed in 2008. The idea of the attack was like this: the attacker, the person who analyzed it, he has seen that we know that the cipher uses a 256-bit key, right? So there are total 2 power 256 possible binary numbers of length 256. So the key will be any one of them, right? That is known to us. Now, when we say you're attacking, we try to reduce the space. So what he did was, he observed that there are some, first he had taken one distinguisher like this. He has taken one distinguisher in third round. Now he observed that if we go from the backward direction, from the output Z, if we go back to the third round, then there are some key bits which has no influence on the distinguisher. Okay. Now suppose the total key size is 256. Among them, we are observing that there are 56 key bits which has no influence on the distinguisher. So the remaining 200 bits are having influence on the distinguisher. So he gave a name for this kind of bits. He called them PNB, which means probabilistically neutral bits. They have less influence. It is not like they have no influence, but they have less influence. So we call them probabilistically neutral bits, or PNBs. Now, what is the advantage of having these PNBs is, since these has no influence over the output or over the distinguisher, instead of going for searching the entire key together, we can just try to find those key bits which has influence. That means the 200 non-PNBs. Okay. Now, what is the benefit? The search space becomes significantly less compared to the previous one, because it is in power. You can see that initially it was 2 power 256 possible option, but now the search space becomes 2 power 200. And after we find these non-PNBs, then you can go for these PNBs, which is even smaller, 2 power 56 only. How much advantage you are getting because of this idea? I will explain with an example. Suppose the key size is not 256, it is 10 only. Okay. There are 10 key bits. Therefore, there are 2 power 10 possible options for the key. So 2 power 10 means 1024. Okay. So initially the attacker knows that the key is any one among these 1024 values, from 0 to 1023, any one of them. Now, if he knows that there are 4 positions which have no influence, he can just ignore those positions, put random values there. He can just focus on the remaining 6 positions. Okay. Now, if these 6 positions can be find out, then the distinguisher will work. Therefore, he only has to find out these 6 positions, which means only 2 power 6. That means 264 values he has to choose. That means he has to choose from 64 values. So initially he had 1024 values, out of which one is correct. Now he goes only 64 values, and out of which one is correct. This is the benefit of this approach. It reduces the search space by drastically. Okay. So using this idea, the attack that this person proposed, Amazon, they were a group of 5 people. They proposed an attack on 7th round of ChaCha. The complexity of their attack was 2 power 248. They introduced this idea called probabilistically neutral bits. The next attack came on this in 2012 from a group of people from China, Shi et al. So they introduced another idea called column chaining distinguisher, and they reduced the complexity slightly. They brought it down to 246.5. After that, the third attack was given by Shubhamay Mitra from ISI Kolkata. So what he showed is that the attacker has the power to choose the key. Okay. So what he showed, that instead of putting random values in the attacker has the power to choose the IV, not the key. Now, instead of choosing random values for the IV, he showed some particular way of choosing IVs, and he showed that if we choose the IVs in this way, then the distinguisher becomes even stronger. Okay. Therefore, we can produce a more strong attack. And using this, he brought the complexity down to 238.9. So it is almost 200 times faster than the previous attack. Okay. The next attack was given by him again with one of his students. What they did was they gave a better distinguisher in the next round. So they took a single bit distinguisher in the third round and converted it to a multiple bit distinguisher in up to 5th round. So they give the first distinguisher in the 5th round of ChaCha. And this also helped to reduce the complexity to 237.7. Okay. The next attack was given by us. So what we did was, we gave an algorithm to find the PNBs. Initially, there was also an algorithm, but we improved the algorithm. And using this algorithm, we made the attack almost 5.32 times faster than the previous one. And after that, in 2020, the last attack which was given, it was almost 2 power 5 times faster than the previous one. It was published in Crypto 2020. What they did was for the first time they observed a distinguisher in the 3.5 round. It was a single bit distinguisher. So using that, they improved the attack by 32 times than the previous attack. Okay, so this is the history of cryptanalysis so far. Next, I come to our research work, whatever we have done in this topic. So our first contribution was, we keep this algorithm that I have already mentioned for the PNBs, and using this algorithm, we produced an attack which was 2.47 times faster for SALSA, and for ChaCha it was 5.0 times faster. And our next contribution was, after finding these PNBs, we showed that instead of putting random values there, we can choose some particular values and put there. And if we do that, the attack becomes further faster. For example, there are 10% of keys for which the attack becomes 8.4 times faster than the previous one. But this is for SALSA, not for ChaCha. Okay. Our third contribution in this discussion was one countermeasure. We provided one small modification in the design, and we have showed that this modification can defend all the known attacks, all the known differential attacks that has been done against ChaCha so far in last 10 years. Okay. Then the fourth contribution was a theoretical work. So the distinguisher that I was talking about on ChaCha and also in SALSA, this distinguisher was experimentally observed fact. So the mathematical reason of this distinguisher was not known. So, but this distinguisher was being used for 12 years for all the attacks. So we, for the first time, gave a mathematical explanation for the distinguishers for both SALSA and ChaCha. Okay, and our latest contribution is this a new attack on this ChaCha, which is 481 times faster than the previous attack. And we have not yet published this work. It is under revision basically. So this is the latest work so far on this direction. Okay, so now we are towards the end of the talk. So what are the future research scopes in this direction? So I have already mentioned that the distinguisher that I was talking about, the distinguisher plays a vital role in the attacks on this cipher, right? If you can find a good distinguisher, then you can provide a good attack. So it is an interesting problem that how to find a good distinguisher, because whatever distinguisher has been observed so far, those are all experimentally observed, right? But if we want to improve the attack, we have to go for higher rounds. We have to, like, so far we have single bit distinguisher only up to 3.5 and multi-bit up to 5 only. If we want to improve to 6 round, then we have to find a distinguisher in 6 round. Then it is the difficulty. Then we cannot go for the experimental observation only, because the correlation becomes so small that it is very difficult to detect any such correlation. Therefore, it will be a great idea if there is some algorithm observed. Okay, because in many other ARX or any other ciphers, people are working on finding algorithms which helps us to find the position where the distinguisher lies. Okay, but no such kind of work has been done on ChaCha so far. So if we can find some algorithm to at least find out the position where the distinguisher lies, then by experimental observation, in a long margin, you can find out a good distinguisher. But just by experimental observation, you cannot improve the distinguisher. Okay, so this is one interesting problem that people can work on, that how to find an algorithm on ChaCha to find a good distinguisher. The next approach can be a machine learning initiative. Recently, machine learning is playing a vital role in cryptography. In 2019, this person Gore, he proposed a cryptanalysis technique using neural networks. So what he did was, using neural networks, he gave one algorithm to find a distinguisher, and this distinguisher was working much better than previously existing distinguisher. So this work he published in Crypto conference. Immediately after that, in 2021, in Eurocrypt, another distinguisher was provided by another group on the same cipher spec it was, and this was also using the neural network. Okay, so this can be another approach, that using machine learning, whether we are able to find out some distinguisher on SALSA or ChaCha, because so far nothing of that kind is there. Whatever distinguisher you are observing for SALSA and ChaCha, they are entirely experimental, by random guessing only. Okay, so these are two interesting problems that we can deal with in future. And the third one is the most vital, which is post-quantum, because all of you know that post-quantum cryptography is a very hot topic now. It is said that if we have quantum computers, we can there are many ciphers which would be immediately breakable. So how much SALSA or ChaCha is secure against this post-quantum cryptography? So there is one algorithm called Gruber's algorithm. So this algorithm says that if we have a function which is unknown to us, but the output is given to us, okay, then from that output we can find using this algorithm, if we have a quantum computer, then using this algorithm we can find the input. That means suppose x is not known, but fx is known to us, then from that we can go back to the input without knowing the function at all. Okay, and for this it is a probabilistic approach, and for this the how many computation, I mean what is the computation required? The computation is if the domain size is n. Okay, that means the function can take n values, the x can have at most n possible values, then only with root over n order we can find out the value of x. That means, for example, if you take suppose the function is, there is a function which has 100 possible inputs. Okay, so for that function, if the output is given to us, this algorithm can find out the input only by 10 operations or some multiple of 10. This is the Gruber's algorithm. Now, using this algorithm, any symmetry key cipher can be attacked, because what symmetry key cipher does is it takes the key as input and give the cipher text as output. Right now, for example, if we take ChaCha takes the key as input. Now the key has size 2 power 256. Right. So if n is the total possible keys, possible values of keys, then for a known ciphertext, we can using this algorithm we can find the key with order of root n computation. So for ChaCha, in ChaCha the key length is 256. So the total possible values of key is 2 power 256. That means the domain is 2 power 256. Therefore, using this algorithm, we can recover the key with complexity square root of 2 power 256, which is 2 power 128, or some constant multiple of 2 power 128. Okay, so but the thing is, even if we can do that, suppose even then the complexity will be 2 power 128, but our present day computers are still not able to go up to this level. That means even if we have a quantum computer tomorrow, still ChaCha will be secure. ChaCha will be secure for now, because the computation speed that we are having in present day, that takes a long time to deal with the complexity 2 power 128. Okay, so ChaCha is still secure, but this can be an interesting approach for research, that whether how can we reduce the complexity further from 2 power to 128. How we can reduce this complexity so that it comes within the margin of our present day computers. Okay, so yeah, so here I will finish my talk. So thank you all of you for listening to me.
Thank you. Thank you so much for your nice presentation. Okay, so here we have a question from Bharat Jati Ranjan sir. Using ML for a cipher, does it increase the complexity?
Using ML for a cipher?
Yes.
So increase the complexity?
Yes.
For attack, you're saying?
Yes.
No. See, what I was talking about whether we can use ML to find a distinguisher. So if we are able to find out a distinguisher, then definitely it will improve the complexity. That means it will reduce the complexity. But so far on ChaCha, we don't have nothing of that kind. But for other ciphers, we have some results like that.
Okay. So any other question from student side?
Okay, IoT. I don't know much about IoT. That's why I don't want to make any comment on this.
Okay. So thank you, Dr. Sabyasachi Dey. So now I would like to request to Alakan Nanda ma'am to vote of thanks for this lesson.
Thank you, sir. It's a very nice topic, Sabyasachi sir. Very nice talk, and you have discussed about the quantum cryptography. Again, it's a very new trending in the cyber security world. So it's very nice talk and nice topic you have presented. Thank you, Paresh sir. You have organized such a beautiful presented such a beautiful topic. And I also would like to thank the organizing team members, Sadapati sir, Bharat sir, and Biswaranjan sir, along with Madhuri madam, to organize such a nice webinar. And thank you all. And it's as it's a quantum cryptography, it is being used, and it is now it's a very new research area, and it can be used in the very new features also. So it's a very informative topic to the students also. So thank you very much, sir.
Okay, thank you very much.
So thank you to all. Then, so we can leave. So, thank you.